Good day and welcome to Big Bad Tech. I'm instructor Jim Pytel. Today's topic of discussion is series and parallel hydraulic circuits. Our objective is to examine series and parallel hydraulic circuits and discuss their observable characteristics and common applications. Additionally, we'll discuss pressure intensification above the setting of the main pressure relief valve. If you've been following this playlist in its intended sequence, up to this point we've been examining relatively simplistic single actuator systems. Today, we'll examine systems making use of multiple actuators controlled by a single valve. Multiple actuators controlled by a single valve can be placed in one of two relationships with one another, in series or in parallel. Similar to series electrical circuits, series hydraulic circuits are relationships where actuators are in line with one another, and one actuator's outflow is another actuator's inflow. Similar to parallel electrical circuits, parallel hydraulic circuits are relationships where actuators are side by side with one another, and actuators share both inflow and outflow paths. Let's examine series or inline relationships first. This discussion operates under the assumption you are intimately familiar with the contents of the hydraulics math, hydraulic cylinders, and Pascal's law lectures, all available at the Big Bad Tech channel. If you haven't watched these lectures yet, or only dimly recall their contents, please take the time to do so now. This schematic indicates a series or inline relationship between cylinder X and cylinder Y in that the outflow of cylinder X's rod end is the inflow of cylinder Y's cap end during the act of extension. Given these are double-acting cylinders, it can be just as easily said that the outflow of cylinder Y's cap end is the inflow of cylinder X's rod end during the act of retraction. Given your understanding of double-acting cylinders, and keeping in mind the incompressible nature of liquid, you should anticipate a unique quality of series circuits, that of near-perfect synchronization. Allow me to demonstrate. As pressurized liquid enters the cap end of cylinder X, it acts to extend the rod X. As rod X extends, a quantity of fluid is simultaneously forced out of the rod end of cylinder X. Given liquid is to be considered incompressible, pressurized fluid enters the cap end of cylinder Y. As pressurized liquid enters the cap end of cylinder Y, it acts to extend rod Y. Although I drew these steps individually, in reality it occurs simultaneously. During retraction, both rods retract simultaneously due to the quantity of incompressible liquid between the linked cap end of cylinder Y and the rod end of cylinder X. During extension, both rods extend simultaneously due to the quantity of incompressible liquid between the linked rod end of cylinder X and the cap end of cylinder Y. The series relationship between cylinder X and Y has therefore served to synchronize the act of extending and retracting their respective rods. Anytime cylinder X extends, it serves to simultaneously initiate extension of cylinder Y. Similarly, anytime cylinder Y retracts, it serves to simultaneously initiate retraction of cylinder X. Furthermore, the series relationship synchronizes the stopping of both cylinders. Given both these cylinders are double-acting, cylinder X cannot extend if outflow from its rod end is blocked, nor can cylinder Y extend if fluid input to its cap end stops. Anytime either cylinder stops moving due to reaching the limits of travel, or perhaps opposing a force in excess of that capable of being generated, it serves to simultaneously halt movement of the other cylinder. The simultaneous extension, retraction, and stopping of multiple cylinder rods can be put to use in such applications as leveling or centering and holding an applied load. While simultaneous actuation is advantageous, series circuits come with complications, notably differences in travel length, actuation speed, and pressure intensification, all of which must be taken into consideration. Let's first discuss differences in travel length and actuation speed for series hydraulic circuits. These observed differences stem from the fundamental volumetric difference between the cap end and rod end of a cylinder. You should understand by now that the cap end at full extension has more volume than the tube-like rod end at full retraction because the rod occupies the center. If you do not understand this difference by now, I need you to perform an abrupt 180 and revisit both the hydraulics math and hydraulic cylinder lecture ASAP. Consider the implication of these inescapable facts applied to a scenario in which cylinder X and cylinder Y have identical dimensions. Let's say the cap diameter of both cylinders is 1.5 inches. The rod diameter of both cylinders is 5/8 of an inch, and travel length of both cylinders is 8 inches. This means the area of the cap end for both cylinders is approximately 1.8 square inches. The area of the ring-like rod end for both cylinders is approximately 1.5 square inches. The cylindrical volume of the cap end at full extension for both cylinders is approximately 14.1 cubic inches, and the tubular volume of the rod end for both cylinders at full retraction is approximately 11.7 cubic inches. Given a scenario in which both cylinder rods are fully retracted, consider the approximately 11.7 cubic inches of liquid on the rod end of cylinder X. When cylinder X fully extends, this same quantity is pushed out of the rod end of X into the full cylindrical cap end of Y. Notice a problem here? Given the cylinders are identical, the tubular rod end volume at full retraction is smaller than the fully cylindrical cap end volume at full extension. How far does cylinder Y extend given full extension necessitates approximately 14.1 cubic inches to fill the fully cylindrical cap end? The answer is not all the way. Given we know the volume introduced to be approximately 11.7 cubic inches and the area of the cap end to be approximately 1.8 square inches, we're in effect being asked to solve for the height of a cylinder. Algebraically rearranging the equation and substituting in our given values, we find cylinder Y to extend roughly 6.6 inches, meaning when cylinder X fully extends 8 inches, cylinder Y only partially extends 6.6 inches. This is to be expected because of the fundamental volumetric difference between cap and rod end of identical cylinders. The rod end has less volume because the rod takes up space. The cap end has more volume because there is no rod to take up space. When you fill the cap end of a cylinder with the same quantity of fluid in the rod end at full retraction, the cylinder won't extend all the way. Additionally, given both cylinders both start and stop extending at the same time, and the fact that they travel different distances in the same time period, this means the cylinders extend at slightly different speeds. Put this in your pipe and smoke it. Then answer me this question. How do you prevent this from happening? The root of the differing extension length and speed conundrum is in the fundamental volumetric differential between rod end and cap end of identical cylinders. So the solution is pretty simple. Don't use identical cylinders. Adjust the size of cylinder Y to account for the differential, such that it fully extends when a volume of approximately 11.7 cubic inches is introduced to it. We can algebraically rearrange the equation and substitute in the given values to solve for the full circular area of our new cylinder Y to be exactly equal to the annular rod end area of cylinder X. Given this is to be fully circular rather than ring-like, we can substitute this area value into the circular area formula and solve for diameter. Doing so yields a cap end diameter for our new cylinder Y of approximately 1.364 inches. Check your work. A cylinder with a diameter of 1.364 and a height of 8 inches does in fact have a volume of approximately 11.7 cubic inches. This means our series relationship of two differently sized cylinders will simultaneously extend and retract a full 8 inches with no differential in speed. Obviously, a manufacturer may not make this exact size, so the next closest commercially available cylinder will have to do. Let's put your understanding of this concept to the test with a brief example problem. Consider a series relationship of two identical cylinders, U and V, with the following dimensions: cap end diameter of 2 inches, a rod diameter of 5/8 of an inch, and a travel length of 12 inches. First, determine how far cylinder V extends when cylinder U reaches the limits of travel in its given configuration. Assume both rods are fully retracted. Next, given the dimensions of cylinder U are to remain fixed, determine the diameter of cylinder V such that it fully extends 12 inches when cylinder U reaches the limits of travel. By all means, pause the lecture and take your best shot. For the mathematically astute, You might also consider alternate permutations of this problem, such as keeping the dimensions of cylinder V fixed and varying the dimensions of U's cap and rod diameter as a bonus round activity worth 0 points. If you perform the calculations correctly, you should have obtained the following area and volumetric values. When cylinder U fully extends, approximately 34 cubic inches is exhausted from the rod end of U and introduced to the cap end of cylinder V. Given we know the volume introduced and the area of the cap end, we're in effect being asked to solve for the height of a cylinder. Substituting in the given values, we find the travel length of cylinder V to be roughly 10.8 inches. Meaning when cylinder U fully extends 12 inches, cylinder V only partially extends approximately 10.8 inches. Given both cylinders initiate and stop extension simultaneously, a property inherent to series relationships, rod U travels a larger distance in the same time span as rod V and can be said to have a faster speed of travel. The differential in travel length and speed can be accounted for by adjusting the size of cylinder V's cap end. Solving for diameter, we find a cylinder with a cap end diameter of approximately 1.9 inches fully extends 12 inches when a volume of approximately 34 cubic inches is introduced into its cap end. Again, a cylinder of these exact dimensions may not be commercially available, so the next closest size will have to do.